Hi, everyone. So today I'm going to introduce this little robot here to you. It's called Dolly. It's a robot sheep, and it follows the first thing that it sees in front of it. So right now it's following this lady because it sees the lady in front of it. And if we move the lady, the robot keeps going after her. So Dolly is not a real physical robot. It's a simulated robot. As you can see, I'm running a live simulation here of the robot. And I'm going to be going over what Dolly does, what software it's running, how it's being simulated. And then we are going to set up some CI for Dolly together. So this is the title of this presentation. Let's set up a simulation-based CI pipeline for robotics together. My name is Louise Poubel. I'm the Ignition Technical Lead at Open Robotics. You can find me on Twitter, Chapolina VR. So let's just get started. First, who's Open Robotics? We are a group of almost 50 people spread around the world. We work on open source software for robotics, like the robot operating system that we will be using today, as well as the Gazebo simulator and the newer versions of both of these. And we also develop a lot of other open source software for robotics in general. So as you can see, we're all over the place. So the software that Dolly is running today is ROS2. So it's the latest version of ROS. And for people who are not familiar with ROS or ROS2, the basic thing that ROS provides you is the plumbing between various parts of your robot. So it provides the publisher-subscriber mechanism, request and response mechanisms. And on top of that, it provides a lot of tools that are running in your robot application. So for example, if we go back there to Dolly, we can see here I have Dolly running inside the simulation, and I also have RViz, which is a ROS tool running here besides it. And you can see the laser scans from the robot showing up on RViz. Oops, I lost my RViz window. There you go. So as the robot moves, you can see that these laser scans kind of move here on RViz, and you can pass pretty much any information from the simulation that the robot's seeing to visualize it with RViz, which is an ROS2 tool. So today we're going to be setting up CI using ROS2, and the version of ROS2 that I'm running right now and that is run in the package is ROS2 rolling, which is a rolling release. It's always in the bleeding edge. It's unstable. It has all of the latest features, but things may break from time to time. But that's the distribution that I chose to work with today, just to live a little bit dangerously. And the simulator that I'm using, that I'm inside it here right now, you can see that the simulation is running live. It's called Ignition Gazebo. It's the latest version of the Gazebo simulator. It's a rewrite with a lot of refactoring of the Gazebo simulator, which itself is almost 2 decades old. And Ignition is the latest iteration. It's what we're running here. It has a lot of advantages and all. I'm not going to be talking about specifically the differences between the old Gazebo or the new Gazebo. I'm not going to be focusing on any of that. I'm going to be focusing on the CI use case and how you can use the APIs of the simulator to set up your CI. The version of Gazebo that I'm using is Ignition Fortress, which is also on my shirt that I'm wearing here. And it's the latest version that we released 2 weeks ago. So it's very fresh. It's our second LTS. We're going to be supporting it for 5 years. And it brings a lot of new cool stuff for people who are interested in simulation. So let's get started here. Before getting into the CI, I want everybody to have an understanding of the system that we have running, so we can understand how we're going to test it, right? If I just show you the tests and run the tests, it's not going to make much sense to you unless you're familiar with the setup. So what is Dolly running? Dolly has a laser scan. So if we check here, I can turn on the visualization of the laser, and we can see here that there are some laser beams that are being shot here in this plane, and some of them return results that are near. This is what we are seeing on RViz. It's pretty much a different visualization of the same thing. So this is just internal to the simulator. So we have Dolly has a laser, which is the only sensor that it has. And it shows what points are closer, what points are further in this radius here. Then the other thing that Dolly has is wheels, because Dolly has to move. So these are the actuators that it has. If we view transparent here and we turn on the joint visualization, we can see these are the two front wheels. These are the ones that are actuated that will move Dolly back and forth and make it rotate. This is just a passive wheel in the back, and this is just the tail for fun. So these wheels are the ones that are going to be moving Dolly, are the actuators, and the laser is the sensor. And connecting them, we have the follow node, which is a ROS node that receives information from the laser, makes a decision. What is the closest points that I have to me? And then it decides on what direction the robot should go and sends that information to the wheels. The wheels decide, well, if I want to go to this direction, I have to rotate this wheel by this speed and this other wheel by this speed. Then the wheels move. As they move, the robot moves in the real world, and the lasers can readings change because the robot is in a new place. So it sends a new laser scan to the follow. And this is the sense, think, act cycle, as we call it in robotics. So it's the robot is sensing the world, thinking about it, making decisions, sending it to the actuators. The actuators are changing the world that generates new sensor data. So that's pretty much the loop that is happening here. And these messages here from the laser to the follow node and from the follow node back to the wheels are ROS2 messages. Here they are ROS2 laser scans, and here they are ROS2 commands. And the important thing to understand here is that everything that is below this line, like everything that is in orange, is being simulated. So the laser here is being generated, like the laser beams are being generated by the simulation, by the rendering engine that is seeing things here and generating it. And the wheel movement is being generated by the physics engine that is connected here to Ignition Gazebo. So if you have a real robot, you would have the equivalents on the physical hardware. You would have a laser driver and the drivers for the motors of the wheels. But the follow node, which is above the line here, and it's in the purple area, the follow node is actually code that would run equally well on your simulated robot and in your physical robot. Because all this follow node does is it speaks ROS2 topics. It listens to laser scans and it publishes commands. So it doesn't know if it's talking to a simulated robot or to a physical robot. It's just speaking ROS2. And it's important to know that, because since we're going to be testing the system, what do we want to test, right? So I put here in green, the follow node is the final goal of what we are trying to test. So think of this scenario. You are developing Dolly, you want to sell Dolly to your clients, and you want to make sure that as you add new functions, you don't break old functionality. That's why you're setting up CI. But the end goal of Dolly is not to be a simulated robot. You want it to be a physical robot. So what you're really interested in testing is that follow node. Of course, you can, it's important also to test the laser and the wheels, usually as a sanity check that you set up the simulation correctly and that you're getting the results that you would expect. But that's not the end goal. We are not trying here today to validate that the simulation is correct. We are trying to make sure that we don't regress on our ROS2 code that we would deploy to a physical robot. That's the goal here. So I put this in yellow. It's not like we wouldn't want to test it. I'm not going to be testing them like doing unit tests for them today. What we want to be testing is the follow node. And another thing important to note is like, well, do we need a whole simulator to test the follow node? Can't we just generate some laser scans, like some mock data, and feed it to that node and see that it produces the commands that we want? Sure. You know, this is also a very valid test case, but there's only so much that you can do with hand-generated mock data, right? You can you can't design like very rich scenarios, and you can't make them very interactive, right? Like, okay, I send this laser scan, and then as the robot moves, how does the laser scan change? The object got closer, or the object itself is moving around and the robot has to follow it. So to create these more complex scenarios, it is important to have a robot simulator that is doing the physics and trying to make things as realistic as possible for you. That's where the simulator comes in. But of course, like, you can also do some unit tests just with mock data, and they can take you a long way as well. So now I told you the high level of what's going on. Now I want to get into a little bit more of the technical details of how this is all being launched and run. So we're using ROS launch to launch everything that you're seeing here. Even like I have a ROS launch for this presentation, and it launches everything that you can see. So it starts with the simulator. The simulator loads up and loads an SDF file with the description of the world. So everything that you see here in the world, the buildings, the lighting, the materials, the behavior of the floor and its friction, all of these details are launched together with the simulator, except for the robot. We launch a world with everything, even the woman is there, but not the robot. Then we use this spawn node to spawn the robot into the simulation. And this is a common pattern that people use in ROS with simulation for a long time. It allows you to spawn the same robot into different scenarios. For example, if you kind of keep it separated, it also allows you to spawn the robot from different sources. So right now, I happen to be spawning from an SDF file that is saved inside it's installed with one of the Dolly's packages, but it could be a URDF file. It could be a robot description that comes through a ROS topic. It could be one that comes from a ROS parameter. So for ROS, it's very important to be able to dynamically spawn the robot inside the simulation. So that's why it doesn't come baked into the world. It's spawned as a node afterwards. And when you spawn it from this SDF file, that's when the laser comes in and the wheels come in, right? The laser is a sensor, and the wheels come with a differential drive plugin that speaks in the simulation language. Then another thing that we're spawning, of course, our follow node, which is our star that we want to test. But at this point, you can see that I put the sheep and the laser and the wheels very deep here into the simulation, because right now they are not running any specific ROS code. There's nothing about them that can talk to ROS. It's all simulation specific that could be used with other controllers, not necessarily ROS. So how does it get to talk to the follow, and then the follow sends the commands back to the wheels? Well, we have to spin up a ROS ignition bridge node, which pretty much takes the messages that are internal here with a library that we call ignition transport, which is a transport library that we use for the simulator, both internally, and you can use it externally as a user of the simulator as well. And it converts those messages to ROS2 and back. So this bridge here is what makes the ROS2 communication possible. So in the end of the day, the follow node is not talking directly to those other two nodes, it's talking to the bridge itself. This is all. I hope it's not too confusing. There are three main things: the laser, the wheels, and follow node, and the robot is spawned live. The simulator is started up with everything that you see in the world. The follow node is spun up there. So these are all the parts that we have to understand. Now, how does a regular I'm going to call it a regular simulation, a simulation that you open with a GUI, like I'm opening here, that it's interactive, that you can pause and play, and it's kind of running in real time. You can see here that it's running, trying to keep the time of the simulation close to the real time. This is regular simulation that you would use for development. But when you're running in CI, you don't want to be spinning up a GUI and like this, like you may not want to be spinning up like the water, for example, because the robot is not interacting with it. It's nice for people to look at, but it's not part of the things that you're trying to test. So what we want to change in the testing scenario is the very first node that we launch. the simulation itself, the environment, is going to be slightly different from the simulation environment for development. In development is this one, and when you're running for testing, we have a test fixture that allows you to in a very controlled way, step the simulation, spawn objects inside it, see how they moved, get the ground truth data that is so hard to get in the real world, and compare it to your expectations. So we're going to be spawning the big green box here is going to be a simulation test fixture instead of the big complex simulation right now. And that's one of the advantages of using Gazebo, is that it's very modular, and you can take and just run the server, just run the test fixture, or just run, you know, the full-fledged simulator with visualizations and debugging tools and connections to rods and all of that stuff. Like when you, another thing that I didn't mention here is that we're also launching RViz, but this is just for demo purposes. It's not really part of the application itself of what, you know, what's happening here. So let's take another look at Dolly before I close the simulation and we jump into the terminal. So let's see again, this is Dolly. It's following the closest point. When the person moves, the robot goes after it. Let me show you the data in RViz changing together. So you can see here that the laser data is moving as well. So I'm going to close this simulation, and we're gonna set up CI for it. So I have here two terminals. So we're going to start, like the one on the top we're gonna use to compile stuff, and the one in the bottom we're gonna use to set up our simulation. I have here what we call a Colcon workspace. So it has, for not to be confusing. So it has the source folder with the source code, install where things are installed, build with build artifact, and log for all of the logging, all of the runs. This is a Colcon workspace. It's a tool that is commonly used in ROS2, but it can be used with ROS1 as well. We use it to develop Ignition. You know, it's very versatile. It helps you set up these workspaces. And down here, it's inside the source folder, and I have the Dolly package here. The Dolly package is just this package here that you can find on GitHub, on my GitHub. There's a repository here, Chapulina/Dolly, where you can get all of the code. So it has all of these directories, and they are just a bunch of ROS packages. So you have the Dolly Gazebo is for the integration with Gazebo Classic, the older version of Gazebo. Dolly Ignition is the integration with the latest one. Dolly Follow is just the follow code that is in a package by itself that it will deploy that to a physical robot. That this package knows nothing about simulation. And we have the Dolly tests package. It's a common practice to put your tests in a separate ROS package so that you, the consumers of your package, like for developments, they don't, you know, or when they want to deploy it or they want to consume it as downstream packages, they don't need to worry about like bring your testing stuff with them. So you put the tests in a separate package. And we also have the Dolly meta package, which if you install just Dolly, you get all of the other ones. So today I'm going to go over the Dolly tests package. So for us to take a look here quickly on what it looks like. So it doesn't have a whole lot of files. There's a lot of metadata, but basically the most important files are the C++ code, which is going to be stepping our simulation and like doing the ground truth checks and moving the robot and so on. It has the launch file that launches launch testing, ROS launch testing, to start up the simulation and do some checks like that the processes ran correctly and so on. We have an empty world specifically for testing that we set up just for the testing. It's very basic. And this is pretty much it. These are the three important files. I'd say that the most important ones are the C++ file and the launch file, but we're going to go over all of them. So I don't want to just show you the ready files. I thought that we could construct them together to get an idea of what is needed. Oh, another thing that is important, sorry, is the GitHub Actions to run those tests live, and those are in the GitHub folder, GitHub workflows. So it's these two files here. I'm going to be showing these to you, but the other ones I'm going to create them together with you. So we're going to create a new package called Dolly tests new. So I'm going to create a new directory and just cd into it. Let's start by the package XML, which is required by every ROS package. So it's an XML file. And it starts with some metadata, but the most important thing inside the package XML are the dependencies. I see a lot of people don't define their dependencies correctly. They miss the dependencies, and that makes tooling a little bit more complicated to handle, or the releasing the packages a little bit more complicated. So be sure to set up your dependencies correctly on your package XML. So I separated them here in a few groups. The amend tools, amend CMake is the build tool that we're using to compile all of this stuff. We have one here to help with gtest. We have 2 linter packages, which I really recommend. I love the ROS2 linter packages. They are super handy. And very efficient and so on. We have a couple of Dolly packages, so we need the follow node, and we also need the simulation, the ignition simulation package. And we had for ROS launch, we need the launch testing, and this is just a CLI, which is helpful if you want to run things by hand. And finally, for Gazebo, we have the bridge. Remember the bridge that connects ROS to ignition, and also the simulator itself. This is Ignition Gazebo version 6, which is the version of Fortress. So our package XML is ready. That's all we have in our package so far. So let's now make the empty world, which let's just get that out of the way because it's a simple file. So just in the worlds directly, we'll put the empty world. So it's an SDF world. So it starts, let me save this and reopen so the highlighting, looks better. So it's an SDF file that has a world tag inside, and we're going to put some plugins and some other stuff inside. So the first thing that we need for simulation, well, we don't need, but it's good to think about your physics. We're setting here the real-time factor to 0, which pretty much tells the simulation run as fast as possible. Don't try to slow down for real time. Like when I was running the example, it was slowing down for real time, just because I'm a human looking at it. I expect things to happen in real time, right? Like, and I also changed the max step size. This is the size of every simulation iteration. By default, it's 1 millisecond. I changed here to 5 milliseconds, so it runs a little bit faster. And I could probably go even higher. Like the higher you have, the less precise the simulation is, but the faster it will run. And for CI, we wanted to run fast because we wanted the turnaround to be quick. So what else do we need here? We need a few plugins. So let's put these 3 plugins here. So the first one is physics. We need physics. Physics is optional in Ignition Gazebo. You can turn it off maybe if you're just doing some sensor data generation, or you're animating something, or you have a different physics that you don't want to use our physics. It's optional, so you can include it here. Then we have the sensors system that will generate the LiDAR data, and that's using the Ogre 2 rendering engine. And finally, we have the user commands system just to receive that spawn command. So the robot can be spawned into the simulation during the testing. And finally, just so Dolly doesn't fall into the abyss, because physics is going to have gravity by default, we add a little ground plane. So you see that I kept it to very minimal. It's a static model that is not going to be affected by gravity, and it just has a collision that is a plane. It doesn't even have visualization. If you try to open this world, you're not going to see anything. There's no light. There's no visualization for the ground plane. It's very plain. It's not for human consumption. It's for CI consumption. Very different from the world that I showed you before. So now let's go to the launch file. So I'll make the launch folder, and we're gonna create the file just with the same name that we have in the other package. So this is a Python file. In ROS2, you can write your launch files in Python or in XML. XML is more for backwards compatibility with ROS1, even though I do think they're slightly different. I don't have a lot of experience writing the XML ones. But here we're going to be using the Python ones. So, just a bunch of imports to begin. And then we have these three important things that we're going to be populating. First, we need the generate test description. This is what's going to describe what we're going to be launching for testing. Then we have one unit test. And from the launch point of view, the unit test is very simple. It's just checking that the process ran, waiting for it to terminate by itself, and checking that it returned a happy code. That's it. So that's what these two functions are doing. Since I'm not testing the ROS messages themselves, I'm not testing a bunch of different ROS nodes. The ROS setup is very simple. I only have in the launch file one test case, but depending on your use case, you may have multiple of these like unit tests in your launch file. So let's open some more space here and let's start with the test description. So what we ultimately need to return is a launch description. If you've written ROS2 launch tests, this looks very familiar to you because every ROS2 launch file needs to return this launch description. Here we have some things that are specific for testing, like to keep the process alive and saying that we're ready. But then we have the four different processes that we want to spin up. We want our test fixture, which is, we talked about, it's the simulator. We want to spawn the robot into the simulation. We want to start the bridge connecting the simulator to ROS, and we want to start our beloved follow node. So let's define these four here, one by one. First, the test fixture is the main one that is different from what you would use for development, right? If you're developing Dolly or any robot, you wouldn't be spinning up a test fixture like this. You would be spinning up the simulator. So all this is doing is, this is the package that we're creating now, right? Dolly package is new, and it's going to have this executable that we're going to generate from the C++ code. It's a gtest executable that runs our tests. So it's going to spin that up. This just starts that, which, remember, it allows us to step the simulation. Then we're going to spawn the robot into that, and it works just like the regular simulation. So this node looks the same if you're spawning into for testing or for development or for any other thing. So we just, we're using the create node that comes from the ROS IGN Gazebo package that can spawn anything for us. It can spawn, like I said before, like robots from topics, from a parameter, for URDF or SDF. It can do all of that stuff for you. It's very handy. Doesn't need to be a robot. It can be like props in your simulation that you want to spawn at runtime. So the bridge, finally, this is bridging those two topics. Remember that we're going back and forth from the simulation to the ROS. So we have the command velocity, the twist messages that are being sent to command the robot, and the laser scans. And this is just bridging them. And finally, our follow node that we spin just like we would spin in a physical robot. Just, we have the summary mappings here because this node is meant to be generic for any robot. So if we want to namespace them with Dolly, we can remap to Dolly. So that's it for our launch description. We have our four pieces. Now let's just populate these two functions, or these two classes down here. This one is just, it's mainly boilerplate code. You just plug in the name of your test fixture here and here, and it's the process that your test is waiting on. And then the other one is gonna check for the return code of your test fixture and just make sure that it returns a success code or a failure code, and it's going to report that to whoever is launching this test. This is it for the Python file. For the launch file. Then let's take a look at our star, the C++ code. So we're going to create this test folder here. Let's see what our tree looks like right now. So we have the package, the SDF, and the launch. Let's edit the C++ code. So we start with just a skeleton here. So I put, you can see a bunch of includes, not gonna go over them. And then inside here, this is, if you've done Google Tests, G-Test, you know, this is a test case, and you can write your code in here. I always start the simulator with maximum verbosity. So you're gonna see a bunch of colorful messages coming up. This is very helpful in CI. So you can see the, like, if something goes wrong, you can kind of track down what was happening before things fail. So I start with the test fixture. So here, we're pretty much in these two long lines, just telling it to open that empty world that we created. This project source path is just a helper function coming from this constant header here that makes it cleaner to find things. If you try to compile this package in a different tree, it still finds things nicely. It's I see a lot of people using just like either full paths or relative paths here. They would work, but then your users are less flexible with respect to where they put those packages, right? The package is not as relocatable. So I like to pass those CMake variables to find the paths. Then we have some variables here that will be populated as we run the simulation. We're going to be counting the iterations of simulation that we're running. We're going to get a world. We're going to get the entity for Dolly, the entity for a target that we're going to put in front of Dolly for Dolly to move towards. And we're going to be storing in a vector all of Dolly's poses a long time and inspecting them and checking that they are reasonable values. So let's set up our fixture. The first thing that we set up, so here fixture, and I'm calling this onConfigure function. I'm not calling, I'm setting it up. I'm passing a function to it. This is a lambda. I'm sorry if people are not familiar with C++. Hopefully this is just like copy and paste, understand the basic ideas, even if you haven't had to handle lambdas. It, like, following the example should be relatively straightforward, I hope, if you don't need to deviate too much from what is here. So onConfigure is pretty much stuff that you want to do once in startup. So we just want to get the world once and store that variable. And then the other callback that we're going to set up here is onPostUpdate. So everything that is in here inside onPostUpdate, so within these two brackets here, this is going to be run for every single simulation iteration. So, you know, here we increment our iterations just to sanity check that we are actually running the iterations that we think we're running. We keep looking for the Dolly model in the world. Remember, the world starts empty and it's going to be spawned dynamically. And, you know, there is a timing thing there. You're not sure, like, exactly at which iteration Dolly is going to show up. Some faster machines, it may show up faster. CI machines tend to be slower, especially the free ones online. So, you know, it may take slower, take less time. I see a lot of people hard coding numbers here. They say, by iteration 100, I have to get the robot. And then it works on their machine, then they put on CI and it doesn't work. So because the CI machine is just slower. So everything that depends on timing, it's good for you to be flexible. That's why we keep looking for it every iteration until we find it. And once we find it, we sanity check that it's being set, and then we start logging the poses. And here we also check the target, which is not going to be there from the beginning. Remember, we only had a plane, nothing else. We call finalize, which calls the configure callback. So at this point, the configure callback has already been called, but we haven't been running the simulation, so the post updates are not being run. So let's run some post updates. Let's run some iterations. Oops, no. So here, we're running it in a loop because we want to run it a few times until the Dolly entity is not a null entity anymore, until we actually got the entity there. So, you know, don't assume it's going to happen immediately. Run it a few times. Don't assume that it's going to happen. That's also important. Put a timeout, because it may just hang here. If there's something wrong with your test, the entity is never going to show up, and you may hang your CI machine for until the timeout of the test framework itself, which may be much higher. So give yourself some timeouts here. Sleep the thread. You don't need to be calling this like as fast as possible. Give it some time and just keep running. Run a few simulation iterations here. It's running 100 iterations every time until we get a robot. Then we do some expectations after this. So, sanity check that we did on timeout, sanity check that we ran the number of iterations that we expected, sanity check that we got the Dolly entity, and that we have more than 0 poses. So some poses were logged. And then since there's nothing for Dolly to follow, we expect Dolly to be spawned into the world and sit tight. Don't move. So we just check that for all of the poses that we logged so far, they are all pretty close to the starting position, which is 0, 0, 0, 0, 0, and 22, just because it's above the ground plane. And this is 0.22 meters. Dolly is a big robot. So let's see now, let's see things happening. So it's like, maybe, let me make this bigger for you to be able to see more. Okay, so I pasted all of this code here now. We're going to spawn an object in front of Dolly so Dolly can follow. And it's kind of like to the front, to the right, so we can at the same time see that Dolly goes to the front and kind of turns towards the right. We describe here the model that we're going to be spawning. Actually, I can remove this visual. See, it doesn't need a visual. Just the collisions, and it's a sphere of radius 1. We create this entity factory message, which is just using ignition transport. We don't need to go through ROS to spawn this. I write more ignition code in ROS, so for me that's easier. I call that service, give it a timeout 2 seconds, wait for it to go, and just check that it succeeded. So that has been spawned into the simulation. And again, we do the same dance that we did before. Let me get this. Oops. So the same dance that we did before. We run simulation in a loop. Remember to reset our sleep. This time we're just running less iterations because we already waited for the service to come back. So the target entity is going to show up there very quickly. Do more sanity checks and check again. Dolly has not moved. The very last pose that we logged is still pretty close to the origin. And the reason why it hasn't really moved yet is because we stopped running, we ran very few iterations and we stopped running as soon as we saw that target. So we can start counting okay, from now on, Dolly is gonna start following. And that's pretty much the rest of the test. So I have a big block of code here for us to go over quickly. So now we run the simulation again, waiting to see that Dolly, I put a condition here, until Dolly moves at least 1 meter ahead, and then we stop. So we know that Dolly is going forward in the X direction. Do more sanity checks. We checked that this time we got at least 4,000 poses. Again, because of timing, it may be a little bit less, it may be a little bit more. So we can't check these numbers for sure. Everything is a little bit asynchronous, just because of these poses here. Then, and because remember, all of these commands are going to ROS and coming back from ROS, right? It's not just running internal to the simulation. So there is an asynchronous component there. Then we start checking the poses. We start checking from 2 seconds, not 2 seconds, 2,000 iterations, which is more than 2 seconds of simulation time. Because remember, we are running at 5 milliseconds time steps. And then we just do some checks that the robot is going forward. The X is always higher than the previous X. It's going right. So the Y is higher than the previous Y. It's turning. And we can see that it's not flying, the Z is not changing, and it's not rolling or pitching, so we can do all of these checks, and this tells us that at a higher level the follow node is working. because when you put something in front of the robot to the right, the robot's pose kind of goes to the right. I'm not doing very tight checks here on purpose because I really want this to be a simple setup. But you may want to have the precise formula that you want your robots to follow, because this is ground truth. Remember, it's as if you were in the real world and you had like access to the millimeter with precision the position of your robot, which is impossible to get in the real world, right? So use this ground truth to your advantage. And finally, I check some like actual values. Here I'm just comparing to the previous post, so it's always increasing or decreasing. And here I check like that the X got to at least 1 meter, the Y, since it's going to the negative Y, it went past 0.2 meters to the right, the Z continues the same and all, and the rotation, also the angle has changed enough. This is our test. It tells us that the follow node is working. Okay, so let's take a quick look. Like we're not gonna write remember that constants file that I told you, just to pass data from CMake to C++. Let's just copy it from the other package and take a look. So it's just CMake define. It's just passing a CMake variable to C++. And finally, let's take a quick look at our CMake lists. We start with, some boilerplate here, CMake version, package, find some dependencies, install the world. We always finish running an amend package on ROS2. And we're going to be filling all of the stuff inside our testing here in build testing. So we start with some linters. Then this is all the stuff to use gtest, and amend provides like really quick ways to work with gtest because it can be a pain in CMake projects sometimes. This is what's passing that variable from CMake to C++, and this is the test stuff. So our test name is follow ignition test. We add an executable. We make sure to link the libraries. We include directories. This is just so we can find this header here that is in the build directory. We're not installing it. We install the test itself, so launch testing can find it. And we also add the launch file for our test. And that's it. Simple, right? It's a lot of boilerplate. It may look complicated if you have to write every single character from scratch, but it is, boilerplate mostly. So let's compile this. I just wrote a bunch of files without, oh, what did I do? Okay. Let's go back to our video. Where am I? It had to happen. 2021. Let me make sure that I have everything sourced. I don't know if I started a new repository. So I'm using ROS rolling, ignition as fortress, and let's click on build. Okay, so it's compiling. You can see that our new package is here compiling. And it compiled. I'm going to show a couple of ways of running the tests. So you can use launch test to run it. First, let me source this repository just to be sure this workspace. So launch test, we can run our tests. Oh, I forgot to source another workspace. And now it should run. There you go. Okay, so this is the test running. You can see that the colorful messages are showing up because we set the verbosity to 4 maximum. So it's gonna run for a while. And while it's running, let's go back to the okay. Let's start adding our stuff. Our new package is added there. While it's running, let's take a look at the GitHub action stuff real quick. It's running on every push and pull request. It's using Ubuntu Focal, Ignition Fortress, ROS rolling, and it checks out Dolly. It checks out ROS Ignition because I'm using an unsupported combination, rolling with Fortress, so I need to build that from source. And finally, it's calling this shell script and passing these environment variables. So let's take a look at the shell script real quick. This is taking longer than it needs to, the shell script, because I'm installing a bunch of stuff, from scratch instead of, I don't know why the test itself is taking so long. So, it's installing Ignition, it's installing ROS. Like, you may want to create your own Docker image that already has all of that stuff in to speed up your CI. I'm creating packages, I'm installing ROS dependencies. This is needed for the rendering stuff to work. See, our tests finished and it failed. I don't know what I did there, but I'm running out of time to debug. Yeah, let's see. We have the simulation running. No. We can run it again, just in case. I don't know what happened. So, the CI is building and then it's testing. I like to put this console direct so you see the messages running and it's selecting all of the Dolly packages to test, and it sends this test results. It's important. So I'm not gonna wait for it to, I probably did something wrong, but I'm running out of time. So I can debug this later. But the Dolly test package itself is what I tried to copy with this one, and that one is working. So since I added all of these files, I'm going to create a new branch. Let's just do ATO live and then commit, add new test package, and then we push. And if we check here on actions, add new test package, it just pushed and it's running live. It's probably going to fail because it failed locally. So you would, try locally until it passes, then you run it on CI. It's failing from very quickly. So, just a matter of debugging. But if you check, the previous commit, for example, on the other branch, it passed, and that's running the Dolly tests package. That's it. I went a little bit over time, but I hope it was worth it.